Welcome to the video on synthetic destruction of ozone. And so we have previously talked about the natural destruction of ozone, but now we're going to be looking at synthetic destruction, and by that I mean things such as CFCs, chlorofluorocarbons, and bromofluorocarbons or halons. Okay, and this chlorofluorocarbon that we're going to be looking at is this one here, where we have chlorine. We're going to have another chlorine there, and a fluorine, and then a chlorine. Let's just double check that. 3 chlorines and a fluorine, yep. So we're going that one there is called, remember how you name these? You do these alphabetical, so you've got 1, 2, 3 chloros. And there's only one carbon, so you don't need to go 1, 1, 1, because there's only one carbon. So it's trichloro, fluoro, and then it's one, so that's methane. Okay. And that one has a shortened name. I'll just double check it here. CFC 11. Then this one over here, the bromine complex we're going to be looking at, or the halon we're going to be looking at, has 1 bromine and then it has 3 fluorines attached to it. So this one here is going to be trifluoro. Oh, sorry, we do alphabetical first, so it's going to be bromo first. Bromo, fluoro, and I'm going to probably run out of room there, so I'm just going to put a dash just to continue it down here. So trifluoro methane, and that one there, halon 13, whoops, 09. Okay. Right, so naturally we do produce some halogenated compounds. We've got trichloromethane, which is CCl3H, and HCl, but as they're produced naturally, they don't make their way up to the stratosphere. They're oxidized in the troposphere. So those aren't really a problem. It's the synthetic ones that are the problems, the ones that we use as refrigerants in the case of CFCs, and propellants in spray cans, and of course halons in fire extinguishers. So let's have a look at what happens when they go up to the stratosphere. Let's do our trichlorofluoromethane. So we've got CL3F. Now that's in the stratosphere, so that's going to react with the ozone. Well, actually, before it reacts with the ozone, it's going to be doing this. It's going to be dissociating, I should say. It's going to photodissociate. Right, so the UV radiation is going to cause it to break apart, and that's going to cause it to make a chlorine radical. Okay, chlorine radical there. And it's the chlorine radical that's going to react with the ozone. Right, just like previously before. I'll put a plus there. Just like previously before, when we looked at natural destruction, we had an oxygen radical. Well, here now we have a chlorine radical that reacts with the ozone, and that's going to cause its destruction. It's going to cause a chlorine oxide radical and oxygen. And that chlorine oxide or radical is going to do more damage. It can react with more ozone, or it can react with a radical of oxygen, and that is going to produce O2, which is nice and fine, but it's going to release the chlorine radical again. And so that chlorine radical, if I can try and find my other colour here, that chlorine radical was what we had at the beginning, and so it's called a catalyst. And so in other words, the chlorine radical that we get from our CFC is being regenerated. It's breaking down ozone to O2, and in the process it's regenerating itself. And so in other words, there's the time in which these CFCs continually destroy ozone molecules is over long periods of time. Okay, and so from one molecule of CFC you can destroy thousands of molecules of ozone, and so that's what you've got to say in exams with these equations to back up what's going on. But you get this, try and show the idea that your chlorine radical is recycled. It's like a catalyst, and from one CFC molecule you get the destruction of thousands of ozone molecules. Now let's have a look at the halon reaction, because the halon reaction is very similar. Okay, so we've got CF3Br. That also undergoes photodissociation, so I'll just put HF, right, to represent the photon. Then we have CF, that's going to be 3, a radical plus a bromine radical. And that bromine radical is going to do exactly the same as what we had with the previous set of equations. It's going to go along and create a bromo radical, a bromine oxygen radical, and cause more ozone destruction. The thing is though, this bromine radical, it's 10 times more powerful than a chlorine radical. And so halons hang around for a lot longer, and they do 10 times more damaging. So they do 10 times the damage compared to CFCs. Now, if we compare CFCs with oxygen, what actually happens is that if we were to draw an energy diagram here with the activation energy, right, to go from O3 to O2, then if we were looking at the oxygen radical, it would have to go over a certain bump or activation energy to cause the destruction of that. If we were to look at the energy for a chlorine radical would be even less, right? And so therefore chlorine is more damaging compared to a normal oxygen radical, so that's why CFCs are a problem. But a bromine is even more so, right? It's even more reactive and does a lot more destruction, right? And so we call or measure the amount of destruction ozone depleting potential, ODP. Now, if I was to look at some examples here from my reference table, because this is not something that you just memorize. So we've got CFC 11, which is what we just did. That has an ozone depleting potential of 1. If we have a look at halon 1301, that has an ozone depleting potential of 10. So, and if we compare that to well, no, we'll just leave it there because all the halons here are significantly more than the CFCs. And so you can see that we have a problem. Houston, we have a problem. So what we've got to do is we've got to reduce the amount of release and use of CFCs and halons so that the environment can recover, because in the next series of videos we're going to be looking at the problems of having an ozone hole and what we have done to try and limit the use of those. And how do we measure it? How do we measure the size of destruction that's occurring in the ozone hole, ozone layer, ozone hole, ozone layer? And so we're going to be looking at those. All right, so hopefully that makes sense with synthetic destruction of ozone, that it is a problem, that you know the equations, and of course the next series of videos will then try and look at what we're doing to measure it, to monitor it, and to fix the problem. See you then.